My name is Ivan Sosnovik. I'm going to talk about the recent applications of scale-equivalent models in computer vision. The research I'm going to present is joint work with Artem Moskalev, Michal Shmaya, and Arnold Smulders. Convolutional neural networks currently demonstrate state-of-the-art results in image classification, image segmentation, object detection, and many other computer vision tasks. Convolutional neural networks consist of convolutional layers, and the core of which is convolution. The convolution of a two-dimensional image and a filter results in a two-dimensional output. To obtain this output, the filter is locally compared to each patch of the input image. The filters are variables that are adjusted during training to increase the performance of the model. The convolution is translation equivariant by design. In other words, a translation of the input image leads to the proportional translation of the output. As a result of this property, the analysis of the original image is as easy as the analysis of its translated variants. Additionally, if the task is to find a certain object in the image, the position of the maximum response in the output is the position of the query object. Translations are very usual transformations of objects in images and videos, but they are not the only ones. Here, we focus on scale variations. Scale changes are very common as they are natural consequences of varying distances between the objects and the camera. Standard convolution is not scale equivariant. As we can see here, both the global and the local structures of the output degrade when the image is downscaled. It would be great to somehow extend standard convolution and to make it scale equivariant as well. In order to do this, we need to somehow work with objects of different sizes. For this needs, we create filters defined on multiple scales. Let's assume that we have 3 scales. We first calculate a basis of two-dimensional functions defined on these scales. The basis is pre-calculated and fixed, and it's not updated during training. We multiply the basis by a set of trainable coefficients to obtain filters that are as flexible as the standard ones, but additionally, they are defined on multiple scales. To perform scale convolution, we convolve the input image with the filter for each of the scales. It results in 3 outputs, 1 output per scale. To build a scale equivariant convolutional neural network, we repeat this operation again and again. The output of this network is 3-dimensional. If we choose the element with the maximum response, we will derive the position of the query object as well as its size. As we can see here, scale convolution is indeed scale equivariant. The global and the local structures of the output stay almost unchanged when the input image is downscaled. In order to understand the usefulness of the proposed method, we start with a relatively simple task, classification of handwritten digits of different sizes. A simple drop-in replacement of standard convolutions with scale equivariant ones leads to a reduced classification error. The scale equivariant network captures all scale variations of the digits by design, while for the standard convolutional neural networks, this is not an easy task. If we switch to natural images, scale equivariant model again demonstrates an improvement over its conventional counterpart. Animals, as well as man-made objects, significantly vary in their appearance. Learning such a diverse set of patterns is almost impossible when the provided data is limited. For scale equivariant models, this task is a bit easier, as all scale variations are properly analyzed by design and do not require intensive learning. We understood how scale equivariance improves image analysis. Let's now consider object tracking. The task is to follow the object in the video. We built a scale equivariant version of a popular CMS tracker. It is trained and tested in the same way as the original one. Due to its built-in notion of scale, the developed model can estimate the size of the query object very accurately, even when it changes rapidly. It was surprising for us, but it also estimates the size more accurately even when no scale changes occur. Scale by itself is an implicit attribute of any pattern, be it as complex as an octopus or as simple as a circle. By making convolutional neural networks additionally scale equivariant, we simplify their learning task. Now, all scale changes are not required to be learned from the training data as they are built in. It allows for more robust object classification, both when the data is limited and when it's not. Moreover, scale equivariant models estimate the size of the object more accurately when it changes significantly as well as when it stays the same. Everything you need to do is to replace the convolutional layers of your CNN with scale equivariant layers. The current most efficient implementation of scale convolution, as well as some examples of its use, are available on our GitHub.